Certain atoms can periodically emit particles, changing their constitution so that they're no longer the same. These atoms are known as radioactive. We differentiate between different radioactive atoms by the particles that they emit, calling them alpha, beta, and gamma decay. Alpha decay is when an atom releases 2 protons, 2 neutrons, and 2 electrons, changing itself into a different atom and a helium atom. Alpha particles are the weakest form of radiation, easily stopped by anything more massive than a sheet of paper. Beta decay is when a neutron in an atom changes into a proton and an electron, the electron of which is invariably released. Of course, because the number of protons is increased, the atom turns into something else. Beta particles are quite weak and can be stopped by thick clothing. Gamma decay is when an excited atom releases a photon and lowers its level of excitement. The atom does not change its number of protons, so it remains the same. These radioactive particles have the most penetrative power. In order to stop gamma rays, it's necessary to wear a thick coat of lead. Nuclear fission is a process by which an atom is split into 2 separate atoms with the destruction of a small amount of mass. According to Einstein's law of general relativity, energy and mass are connected. The destruction of a small amount of mass releases an incredible amount of energy. In an atomic bomb, large amounts of fissionable material are contained, so that the neutrons released by one fission triggers several more explosions. In an atomic power plant, control rods collect the neutrons at a rate that allows a steady amount of fission reactions. Nuclear fusion is a process by which 2 atoms are smashed together to form a larger atom that weighs less than the sum of its component atoms. This loss of mass generates energy in a similar way to nuclear fission. However, the byproducts of fusion are not radioactive like fission remnants are. It also could use cheaper fuel than fission, making it a preferred source of electricity, once it's developed to be productive. While scientists have developed new fusion reactions, they required more energy than they released. This makes fusion an unusable source of energy at the moment. Of more use to us in our daily lives is a thorough understanding of mixtures and compounds. A mixture is a gathering in close accord of different materials or elements. Mixtures in which all the components are easily separated visually from each other are known as a heterogeneous mixture. A delicious example of a heterogeneous mixture is a pizza, which has obvious components like pepperoni, crust, sauce, etc. A homogeneous mixture has components that are not easily discernible from each other. Another example is lemonade. While you might be able to remove the lemons from the top of the glass, you cannot strain out the flavor from the water easily. This is different from a compound, which is a chemical combination of different elements. Compounds are formed when different atoms bond together. Common compounds are water, salt, and carbon dioxide. Elements can bond via ionic or covalent bonding. Ionic bonds are caused when an atom gives an electron to another one. This causes one to have a positive charge and the other to have a negative charge. This causes them to attract each other, like a sock to a piece of laundry. Covalent bonding is when 2 atoms share a pair of electrons. This is caused by the octet rule, which says that an atom that does not have 8 valence electrons seeks to be so. For instance, carbon has 4 valence electrons, while hydrogen has 1. The octet rule states that the carbon will attract and bond to 4 hydrogen in order to bring its valence electron count to 8. Minerals are composed of all those elements and compounds. In appropriate conditions, they form specific patterns. Many of us have seen crystals. These are natural formations of the mineral that the crystal is composed of. Minerals are not only seen manifested in crystals. Rather, they are only rarely composed in such awesome formations. In our daily life, we usually see minerals in their most common formation as rocks. Rocks themselves are an interesting study. They're usually classified by their method of origin. Igneous rocks are formed by fiery origins in the bowels of the earth. They're usually formed of cooled magma. Other rocks are formed by the deposition of sediments over time. Common examples are sandstone and shale. While this is exceedingly less common in the makeup of the earth than igneous rock, people are most familiar with this rock since it composes most of the very outer crust. Metamorphic rocks are those sedimentary or igneous rocks that have been subjected to incredible heat and pressure to change their composition. This usually occurs far below our feet. Humans are relatively well acquainted with the externals of the Earth, but none have witnessed the internals of the core of the Earth. In short, we live on the crust of the Earth. This is only a couple dozen miles thick at its thickest. Below us we have the mantle. The mantle is composed of a near molten rock that is commonly fired out of volcanoes as lava. Between the crust and the mantle is a more discontinuity, which marks the sudden change from the crust to the mantle. Under a mantle is a core, which is theorized to be composed of metal instead of the rocky material of the mantle. Pressure keeps the inner core of the Earth solid, but the outer core is molten. An important feature of the crust is that it isn't a solid mass. Rather, it is composed of plates that float on the mantle. These plates slowly move around according to the theory of continental drift. Over time, the continents move, at the rate of inches per year, into new formations as the mantle flows underneath the tectonic plates. At the edges of these plates are popular locations for mountain ranges, deep ocean trenches, powerful volcanoes, earthquakes, and so much more. While the tectonic plates are to blame for many of the most stunning natural formations, they are all changed and affected by surface processes that gradually remove some of their glory. Weathering is the way that rocks are gradually ground to piecemeal. Mechanical weathering is usually water creeping in between rocks and freezing, eventually breaking the rock apart. Or a glacier may come blazing through and tear the rocks to pieces. Chemical weathering is also a common process. Water can combine with other compounds or elements to create a corrosive mixture. This is a picture of a limestone gravestone. Limestone is a highly reactive stone, which makes it very susceptible to chemical weathering. Erosion is especially common. Who hasn't seen how a river is carved by the water flowing through it? Whenever water travels anywhere on the ground, it is affecting in some manner the ground it travels over. It does this through the suspended load, dirt that is discoloring the water, or the bed load, rocks that are too big to be suspended but are gradually pushed along by the water flowing over the top of them. When the river or stream eventually reaches the ocean, it deposits all the material into the ocean, potentially billions of tons of sediment worldwide. Whenever the ground moves as a result of erosion, it's known as mass wasting. Many forms of mass wasting are nearly invisible to the eye. It can be as simple as your gravel driveway gradually getting thin at its highest point. Others, such as mudslides, are catastrophic and make obvious lasting changes on the environment. On the other hand, serious problem occurs when too little water is in the area. Groundwater reservoirs that have lasted for hundreds of years are being depleted at record paces. This raises the threat of water being depleted in areas in a few years. Many of the farming regions of the United States are irrigated almost exclusively from groundwater deposits from the age of the last ice age. In some areas of the United States, water deficiency is so dramatic that the ground has literally fallen, in some cases dozens of feet over 50 years. When these water deposits are dried up, what shall we use to irrigate our crops? Another interesting focus of physics concerns the systems that we use to read the history of the Earth. What has happened in the past makes for an interesting subject of study. Much of this involves studying the rocks of Earth. For instance, sedimentary rocks are developed in horizontal layers. If they're not in a horizontal direction, they must have been moved after they were formed. Also, because sedimentary rocks form from the bottom up, the farther down that you go, the older the rock is. Finally, if igneous rock from a volcano cuts through an area of sedimentary rock, the igneous rock is younger than the rock that it cut through. The same theory applies to fault lines. If the fault cuts through something, it must be younger than the rock that it cut through. Another technique used to estimate the age of a body of rock is through the fossils that are discovered in it. For instance, the fossils of trilobites are quite common in a certain age of rock. There are 4 different ways that we can see a remains of early organisms. First, we can occasionally see the actual organism. This is exceedingly rare, but has happened, as in the case of some woolly mammoths that we found frozen in Russia's permafrost. Other common examples are fossilized insects that are trapped in amber, or fossilized tree sap. In other cases, we cannot find the actual organism, rather fossilized remains. What this means is that over the centuries, minerals such as silica gradually replaced the bones and hard remains of the animals. These are one of the most common types of remains. Sometimes, instead of the bones of organisms being filled in, the bones simply decompose, leaving a hollow mold of where the organism was. Birds appear especially prone to this type of fossilization. Similar type of fossil to the mold fossil is a trace fossil. These are fossils of prehistoric animal tracks, borings or tunnels, or burrows. Through these fossils, we can find out specific information about the animals. While we can find out the relative ages of these animals through the rocks that they're buried in, we cannot find their exact ages through this method. In order to find that information, scientists depend on radioactive dating. It's well known that there are amounts of radioactive elements everywhere in our environment. Plants and animals absorb these radioactive elements. However, when we die, scientists can use the known half-life of the element to tell how long it has been since the organism was alive. Problems and inaccuracies can still come from radioactive dating because it depends on two things: that the amount of radioactive material started out with is known, and that nothing has removed some of the radioactive element. If either of these two problems have occurred in the sample, then the dating of it will be inaccurate. However, using fallible human tools and resources, can we expect any better? We can never hope to learn everything about this massive universe, but scientists seek every day to find out more of the world's secrets. There's still so much that we don't know about this crazy universe.